Our first speaker today is Dr. Sangeeta Yadav. She would be talking to us about data-driven stabilization schemes for singly perturbed partial differential equations. She is a PhD graduate from the Department of Computational and Data Science at the Indian Institute of Sciences, Bangalore, India. Her PhD research was focused on advancing scientific machine learning and developing cutting-edge AI-based PDE solving techniques. She's currently working as a research scientist at the same institute. Earlier, she was briefly working at Qualcomm Research and Development on auto-tuning camera filter parameters. With that, please join me in welcoming her for the presentation. You may want to share your screen.
Hi, everyone. Thanks a lot, Sundata, for that introduction. I'll just share my screen. Yeah, can you guys see my screen?
Yes.
Like clearly?
Yes.
Fine. So today I will be discussing about data-driven stabilization schemes for singularly perturbed partial differential equations. And I've done this work during my PhD under Professor Sashi Kumar Ganeshan's guidance at the Department of Computational and Data Sciences at Indian Institute of Science. So here we start. So in this course of presentation, firstly, I will introduce what singularly perturbed PD is. Few of you may already be aware of these terminology, but for the others, I shall start from a very basic introduction. And then I will introduce the audience to what a stabilized finite element method, especially a streamlined upwind perturbed Galankin scheme is. And further, I'll detail about a neural network, SPDNet, which I have developed during my PhD for predicting the stabilization parameter, and then SPDNet, and then I'll discuss SPD-ConNet. And in the final stage of the presentation, I will show how to use SPD-ConNet for a variable convective velocity cases, and then I'll conclude the presentation. With that, in my PhD, I especially focus on convection diffusion equations. And since these equations have a lot of applications in numerous areas, such as in modeling water pollution problems, oil extraction, and designing convective heat transport, and defining continuity equation in semiconductors, in modeling chemotaxis in bacteria, and chromatography, and in image processing, wherein paranormalic equation is a convection diffusion equation. And for a very general audience, convection is nothing but the flow of a particle under the influence of another force, and diffusion is the spread of a quantity from the region of higher concentration to a lower concentration. Here, this is a convection diffusion equation, and which will be the focus of today's presentation. The first term is a diffusion term, and the second term is a convection term. Here, epsilon is a diffusion coefficient, and B is a convective velocity. F is the source term, and we are trying to obtain U in domain omega, and the value of U on the boundary of omega is UB. Today's presentation is all about singularly perturbed differential equation. So what is singularly perturbed differential equation? So these are the equation wherein they have some either coefficient or parameter, and depending on the value of that parameter, the solution of the equation can start behaving abnormally in some way. Either it can have oscillations, or it can have boundary layers, interior layers, anything, and because of which the numerical technique, the conventional numerical technique are inadequate to solve these equations sufficiently. For a model problem, herein we can see it is a second order one equation in a one-dimensional domain from 0 to 1, and the value of U on boundary 0 and 1 is equals to 0. Let's say for this equation, if I set epsilon, which is the diffusion coefficient, equal to 0, then what will happen? In that case, this term will be negligent, and the equation will be reduced to a first order ODE. And the solution of this first order ODE will be Ux is equals to X. But if the solution is equals to x, then it won't satisfy these boundary conditions. That is, u is 0 at 0 and 1. Because for ux is equals to x, the value of u at 1 will be 1. So that's what happens so when we have epsilon very, very small. And for this equation, for epsilon equivalent to 0, this problem will have no solution in C101. So from this, we can infer that whenever epsilon is near 0, the solution behaves badly in some way. And these type of differential equations are called singularly perturbed differential equations. Most of the singularly perturbed differential equations have a boundary layer in the numerical solution. And by boundary layer, what I mean, this concept layer means narrow regions where the solution has steep gradients. For example, for the numerical solution, for the analytical solution of the previous equation, we'll check why and where the boundary layer comes. So this is the analytical solution to the earlier equation. For this, if I check the continuity in the solution in the entire domain from 0 to 1, excluding 1, this continuity exists for all the value of epsilon, even if it is very, very small. Whereas the moment I check this continuity near x is equals to 1, I see a discontinuous limit, which means near x is equals to 1, there is some discontinuity, or we can say there is a region where the solution has a steep gradient. And this steep gradient layer region is because of which the boundary layer will come. So here in this diagram, we are plotting two things. The first one is the analytical solution, which is shown in red, and the blue one is the Galerkin solution. In the Galerkin solution, we can clearly see the oscillations. And these oscillations are coming because of a boundary layer near x is equals to 1. And this boundary layer is coming because the epsilon is very, very close to 0. And due to this boundary layer, we are seeing spurious oscillations. So as to get rid of these oscillations, often stabilization techniques are used in literature. But most of these stabilization techniques are dependent on a stabilization parameter, which is in general difficult to find. And in this work, we are focused on finding an optimal value of stabilization parameter. These are three categories of the techniques which are in general used to solve any singularly perturbed differential equation. The first class is the conventional numerical techniques such as finite difference method, finite element method, finite volume method. But since all these, if we use any of these three techniques, we see spurious oscillations in the solution. So we use stabilization techniques such as local projections, streamline, upwind, Perturbed, Galerkin, and many more. And then there is a third category of equation techniques, which are neural network based PD solvers, which are very famous or very common these days, popular these days, such as physics informed neural network, and a few more extensions of physics informed neural network, DeepNet or Fourier neural operator, and many more. But none of these categories of technique is sufficient for solving singularly perturbed differential equation. Why? In the first category, we see spurious oscillations. In the second category, which is stabilization techniques, we can get rid of the spurious oscillations, but these techniques are dependent on a stabilization parameter, which is difficult to find. And the third category of techniques, they perform good for a simple class of PDs, but when there is a boundary layer or if there is some kind of non-regularity in the solution, then these techniques are inadequate, like physics informed, DeepNet, and Fourier neural operator, three of them, all of them. Sorry. Herein, I can show you the spurious oscillations in the numerical solution coming from the Galerkin finite element technique. By Galerkin, I mean a very basic finite element technique. So here for this polygonal mesh, if I solve a 2D similarly perturbed differential equation for which this is the exact solution, we can see this is how the unstabilized solution looks, and this is how a stabilized solution looks. The first class of methods, which we will be later on using on to compare our proposed technique, is physics informed neural network, which this group is very familiar with. Not familiar because this group is responsible for developing this technique. And in physics informed neural network, we just write any PD as LU equal to FT, where L is a differential operator and U is the solution which we are trying to obtain. And then we approximate the solution U with a U theta, where theta are the parameters of the neural network, and the loss function which we use to minimize, which we minimize with the neural network is given as here. Here the first term is the strong residual of the equation, L2 norm of the strong residual, and the second term is the is for the boundary loss, where the UV, the value of UV is given to us. Here NU is the number of collocation points used to evaluate this PD, and X and Y are the coordinates. Just a clarification. Are you guys seeing extra screen on my presentation, like this
No.
grid with all the participants?
No.
Okay, fine. Thank you. Okay, as I already mentioned, so these data-driven PD solvers also have their own limitations on SPD. Like, first of all, they have high computational cost because the computational cost scales with the number of collocation points in the domain. And second, they are sensitive to initialization, and they have a lack of interpretability also for the less regular solutions. And similarly, Fourier neural operator also has its own limitations. So in this work, our objective was to get rid of the limitations of both the conventional numerical scheme as well as a data-driven, as well as the limitations of the data-driven PD solvers. For the conventional numerical scheme, the limitation was to come up with an optimal stabilization parameter for a stabilization scheme. And for the data-driven PD solvers, we have to come up with a better loss function which can cater to the singularly perturbed cases. So we thought, why not to use the advantages of both the worlds and come up with a hybrid scheme which can leverage the benefits of neural network for approximation of the function and the structured definition of elements and mesh and the stabilization from the conventional numerical scheme. So in this work, we will be trying to predict the value of the stabilization parameter using a neural network. And therein that stabilization parameter will be used as it is in the stabilized finite element method structure. And from this proposal, our objective is to develop a technique which is capable of computing the boundary layers or interior layers sharply and accurately. Though there are many stabilization techniques available in the literature, like orthogonal subgrid scale, continuous interior penalty, local projection stabilization, and streamline Upwind-Petrov-Galerkin. But herein we have only focused on streamline Upwind-Petrov-Galerkin scheme because it's very popular in the context of finite element method and the singularly perturbed differential equation cases. Before going into the deep details of the proposed scheme, I'll first explain the basic finite element technique, the way we use it for solving singularly perturbed differential equation. For a given SPD, so from now on, I'll call the singularly perturbed differential equation as SPD. So as to solve any SPD, we will be trying to find U such that for all test functions V coming from the Sobolev space H10, this bilinear form satisfies. And in this bilinear form, AU comma V is nothing but we take the equation, we multiply it with a test function, and then we integrate it over the whole domain. And then then the second order derivatives reduces to first order derivative by applying the integration by part technique. So here we can see AU comma V is epsilon U dash V dash, and V is the convection velocity, and it is U dash V dash, and F comma V is FP, integral of FP dx on the domain omega. In the Galerkin V, if we use Galerkin V form, we already have seen that we get spurious oscillations in the numerical solution. And so as to get rid of the spurious oscillations, we add this residual term to the weak formulation. So this RU is the strong residual of the given PD. We add this term here after multiplying it to the streamline direction. By streamline direction, I mean B dot grad V, where B is the convection velocity and V is the test function. This whole stabilization term is multiplied by a parameter, stabilization parameter, tau y. Tau I is of very importance in streamline upwind perturbed Galerkin scheme. Why? Because a small value of tau I can still show you some oscillations in the solution, whereas a bigger value of tau I will give you an overly smeared solution. So we have to come up with the way we have to come up with an optimal value of tau such that neither it has oscillation nor it has extra smearing in the solution. Now we are trying to find a general form for tau. The thing is, the first question will be like, is there no formula for tau I in the literature? Yes, there is a formula for finding out the stabilization parameter for streamlined upwind perturbed Galerkin scheme in the literature, which we can see here. Here, P is the Piclet number, which is BH by twice epsilon, and tau stabilization parameter can be expressed as H by 2B cot hyperbolic function of Piclet minus 1 by Piclet number. This formula gives the exact solution only for the one-dimensional problems. It is not directly extendable to 2D or 3D. And secondly, this formula is not applicable to complex cases of non-uniform meshes or other issues. So we aim to develop a neural network model to identify an optimal stabilization parameter for in general for all the 2D and 3D cases and for complex problems as well. And from this formula, we can deduce that the tau, the stabilization parameter, will be dependent on the mesh size h, the convection velocity b, and diffusion coefficient epsilon. In my PhD, I have developed 3 techniques: SPDNet and SPDNet, which is an ANN for solving one-dimensional SPDs, and SPDNet2 for 2-dimensional problems, and SPD Convest, where we have wherein we have proposed a convolutional neural network for predicting local cell-wise stabilization parameter. In SPDNet, we have developed an ANN-based supervised and L2 error minimization techniques for predicting the tau. We have also developed a training dataset based on the equation coefficients and demonstrated the prediction of global and local variants of tau with an ANN. And finally, we have showed that ANN-aided AFM solvers solve one-dimensional SPDs with lesser numerical error than that either with a pure neural network solver or with a conventional SUPG stabilized finite element scheme. This is how we have formulated the problem of finding tau I as a regression problem in SPDNet. We express tau I dependent parameterized over theta. Theta are the weights of the neural network G, and we pass epsilon b and h as the input to the neural network. Therein we obtain tau I hat, and this tau I hat is substituted in h. In H, we are trying to find a SUPG FEM solution for the given problem. Once we obtain UI hat, which is the SUPG solution from the predicted tau I hat, then we consider 2 kinds of loss functions to learn the neural network weights. The first one is a supervised technique. So the first question which will come to your mind will be like, if we are using supervised technique wherein we know the formula of tau I, then why are we doing this entire exercise? Like, if the formula is known to us. This supervised technique is only developed to create a baseline case so as to understand the approximation capability of our neural network. In the second technique, which we call as L2 error minimization scheme, herein we try to minimize the loss between UI hat and UI. Here UI is the analytical solution of the problem. So the second question in your mind will be like, if we know the analytical solution for the problem, then why are we doing the entire exercise? The thing is, both these techniques were developed as a proof of concept for one-dimensional equations. And we had a plan that if at all we get a success here, then only we will extend it to 2D. And in 2D, we will not use either a formula for stabilization parameter or any analytical solution for the equation. With that, this is the network architecture for SPDNet. Herein we batch our input into pairs of epsilon b and h. Then we pass it through a neural network, which is a very basic neural network of just 3 layers with 10 hyperbolic nonlinearity. It's a very basic neural network because the problem at hand is not complex in the term of the regression. It's only the loss function designing which is a complex part here. So from this neural network, we obtain a normalized stabilization parameter tau. And this stabilization parameter tau is used for three kinds of experiments. The first one is the supervised technique, wherein we use root mean square error between predicted tau and the tau, which is coming from the standard formula, which we have seen earlier. The second experiment is the tau global experiment, wherein we substitute normalized tau in and obtain SUPG solution from it. And further, this SUPG L2 error between SUPG solution and the exact solution is used to learn the weights of the neural network. The last experiment was of tau global, wherein we predict two values of tau, tau1 and tau2, and then we localize it over the entire domain by multiplying it with matrix M, and then we get tau I equal, the dimension of tau I are equal to the number of cells in the domain. And from this tau vector, we predict, we get the solution, SUPG solution for the given equation. And this SUPG solution, the L2 error between this SUPG solution and the exact solution is used for as a loss function for the neural network. Any questions so far? Please let me know if I'm like, if you guys can hear me and if I'm there.
Yeah, we can hear you. No worries.
Thanks, Sangeeta. Yes. If not, then I'll just go further. Yes. So herein, this algorithm is for L2 error minimization scheme of SPDNet, wherein for all the epochs, we in the batches we predict tau hat, and this tau hat we use for calculating this solution U hat, and then then the loss is nothing but the integration of U hat tau hat minus U, where U is the analytical solution, and then we minimize this loss. In the L2 error minimization scheme, as I already explained, that we have two kind of variants. First one is a global tau, wherein we predict a single tau for whole domain. And second is a local tau, wherein we predict two values, tau1 hat and tau2 hat, for non-boundary and boundary layer regions, because we thought that in the standard formula for SUPG, there is no way of getting two different taus for boundary and non-boundary regions, whereas in our opinion, there has to be two tau, because non-boundary region and boundary layer region needs separate kind of treatment. And for that, we predicted two values, tau1 and tau2. And then we multiply it with matrix M. In matrix M, we have two columns, one for the non-boundary tau and second for the boundary tau. In first column, we have taken one wherever there is no boundary. And in the second column, we substitute one for the boundary layer region. When we multiply this matrix M with the predicted tau hat, we obtain a localized stabilization parameter, tau local hat. For these experiments, we will be using two kind of evaluation metrics. First one is RMSE error between tau hat and tau, and second is L2 error between the SUPG solution from predicted tau hat and analytical solution U. Here we can see the qualitative comparison of the solution which we have obtained from these 5 schemes for the test case when epsilon is 10 to the power minus 11 and B is 1, H is 0.0083. Epsilon 10 to the power minus 11 is a very, very perturbed case. As you can see, epsilon is extremely small. And herein we are comparing the solution from supervised technique, L2 error minimization tau global, L2 error minimization tau local, analytical solution, and the solution from the PINS technique. So here we can see among all the other techniques, only L2 error minimization tau local solution is standing out because it's a bit far from the analytical solution. And this is an open question for us, like why is it happening for the local case? But in the case of tau global and supervised, you cannot see any gap because both these solutions are overlapping each other, which means that the performance of tau global is comparable to the performance of supervised technique, which gives us a confidence that yes, if we use tau global technique, then we can do at least as good as what the existing formula was doing for this. Herein we are in this table, we compare the performance of these 4 techniques for validation data and test data. In the first column, I'm showing the L2 error in the numerical solutions for pin supervised L2 error, L2EM local and L2EM global. And we can see L2EM global technique gives the least error out of all. And secondly, we compare the RMSE error between the tau hat and tau. In herein, we are not showing it for pins because pins doesn't have any stabilization parameter. And similarly, tau local, it has stabilization parameter, but the size of the stabilization parameter is equal to the number of cells. So we could not compare it against the standard formula. That's why these two rows are blank. But if we compare the supervised and L2EM global techniques performance, then we can say they are just one order apart. But for the test data, we can clearly see that the RMSE error between tau hat and tau is of the same order. And also the L2 error between the solutions is, in the case of L2EM global technique, is better than any of the above given techniques. So it was this comparison that which gave us the confidence that yes, this technique is workable for singularly perturbed cases, and it will be advantageous for us to include it in the literature. And with that motivation, we plan to extend this work for the 2D and other complex cases. We have done few more experiments in the 1D case. The first one is wherein we have divided the data. The data was a set of pairs of epsilon, B, and H, where diffusion coefficient, convection coefficient, and the mesh velocity. When we plotted the value of standard tau with epsilon for different epsilon, we could see that up to 10 to power minus 7, we don't really see any difference in the value of stabilization parameter, because these cases are so critical that the difference in the value of the stabilization parameter is so minimal that you cannot even figure it out in this diagram. So we thought that it's better to divide the data in critical and non-critical parts so that we can see the performances clearly. So we have splitted the data here at 10 to power minus 7, and the range from the range of epsilon from 10 to power minus 16 to 10 to power minus 6 will constitute the critical data and further non-critical data. Because anything greater than 10 to power minus 7, there the equation will not be singularly perturbed anymore. So we don't really need any good performance or a stabilization parameter there. Here for the critical and non-critical test set, we can see the performance of the SPDNet in terms of the predicted stabilization parameter tau. So we can see the value of L2EM local is very far from the other three techniques, but the supervised and the L2EM global are pretty close. And herein for the non-critical test set, everything overlaps each other, because any value of stabilization parameter is good for the SUPG scheme. For the critical data set, in terms of error, we can see supervised and tau global are performing similarly, but tau local is at least one order worse than the other two. For non-critical test set, doesn't matter. Now we also conduct a mesh refinement analysis for different number of cells, and we saw that the supervised and semi-supervised global technique here, they perform equally good, but the semi-supervised local technique performs good only when the mesh is coarser. With that, after doing all those experiments and doing the performance check in the one-dimensional case, then we moved on to two-dimensional case. And herein the difference especially lies in what we consider for as a loss function. Here, this is a 2D convection diffusion. Here B can be a vector depending on X and Y. So in 2D, we have few more challenges than what we had in 1D problems. The first one is the presence of the crosswind direction convection velocity. And because of this, we will see extra spurious oscillations. And secondly, in 2D, most of the time, there is no closed form analytical solution available for training. And third thing, the accuracy of the stabilization parameter here will be extremely low. For one-dimensional case, SUPG performs even the existing stabilization parameters formula performs really good, whereas for 2D it doesn't. And last, it also has interior layers in the solution in addition to the boundary layers. So for SPDNet, for the 2D problems, we have proposed a neural network which we call as SPDNet 2. And in this SPDNet2, we are using a loss function which is based on the a posteriori error estimators. And this loss function proves naturally better for the application for SPDs. Also, we are including a gradient normalization scheme for the stabilization parameters so that we can treat the interior or boundary layer regions adequately. This is SPDNet2. In SPDNet2, tau theta is dependent on epsilon, b, and h, and we use this tau to get the SUPG solution u. And in the loss function, the first term is the strong form residual of the PD as we use in pins. And the second term, this term is very important. This term takes care of the smearing in the solution, and we call it as a crosswind derivative term, because herein we are using B perpendicular, which is B2 comma minus B1, and we are taking a dot product of this with grad u, and then we substitute it, then we inputted it to the function Q given as this. So this term will take care of the smearing in the obtained solution. And we will try to get theta star as the argument for loss function. So here in SPDNet2, first we take input
I have a query.
Yeah, sure.
In the previous loss function.
Yes. Yes, Sangeeta.
Yeah, previous slide.
Yeah, I'll just move to previous. Yes, this thing.
The square term is that the last square term is at whole, or is it?
Oh, sorry. It is. I'm sorry. It is just with the crosswind derivative term. Thanks a lot for.
Yeah, it's a regularizer basically.
Yes, it's kind of regularizing.
Okay, thank you.
Thank you for pointing it out. Yes, in SPDNet2, we are starting with the input I, which consists of epsilon b1. B1 is the velocity in convection velocity in x direction. B2 is convection velocity in y direction, and h is the mesh size. Then we calculate Piclet number for this input I, which is bh by twice epsilon, and then we substitute this Piclet number in the neural network G, and then the predicted tau is divided by the gradient of the Galerkin solution, because the gradient tells us where wherever there is a higher gradient, we assume that there is a probability of having a boundary layer or interior layers. So by dividing the predicted stabilization parameter by gradient of u, which we call as the gradient normalization, we obtain a local stabilization parameter for the problem. Here Q function is given as this, and B, the crosswind direction is B2 comma minus 1 divided by norm of P. And the loss function is given as this, the strong form residual and the crosswind derivative term. This is the architecture for the SPDNet2. We pre-process the input to obtain Piclet number, and the Piclet number is passed to a neural network, and then we obtain tau hat. This tau hat is normalized, the gradient normalization is done, and then we get the solution UH, and then we calculate loss and back propagate it until the convergence is achieved. So as to compare the performance of SPDNet2, we are considering 4 kind of baseline schemes. The two are
Kamal here again. So I have one more query in the previous slide.
Yes, Kamal. Thank you. Yes, Kamal, are you saying
something? The previous slide.
Yes.
So this is pin, correct?
Sorry.
This is the loss function is a pin loss function. So why epsilon to be an input?
Yes.
So what is the range of epsilon? Like, are you solving for multiple epsilon at the same time?
No. It's not. There is no concept of training and inference here. Here we are considering it as an optimization problem. So given a PD, we solve it just for that PD.
So it's a single value. So why to be an input to the network? Epsilon is only one number, correct?
Yes, it is one number. The thing is, here we are not trying to obtain U. Here we are trying to obtain tau, and tau is only dependent on epsilon, B1, B2, and H.
But if it is not parameterized epsilon, then why to make as an input? It can be on the equation itself.
Yes, it can be in the equation itself, but here we are just solving it like an optimization problem. So the network, or you can directly say it, that we are just using the steepest gradient descent as an optimizer. There is no concept of generalizability.
So U as the network input is constant, basically.
Yes, the network input is constant. Yes, it is constant.
So if it is constant, So if it is constant, why to be a input to the network? It can directly come to the loss function.
It can directly come to the loss function, but then the U is dependent on epsilon B and H, because the numerical solution which we obtain depends on epsilon B and H.
But you're not parameterizing epsilon, so I don't know, if I miss something.
No. Whatever you are thinking is correct, actually. Your question is also good. So here, like if you compare it to any general neural network, therein what we do, we take a few examples of like input parameters, and then there is some data given to you. But in this case,
Yeah.
we have modeled it as an optimization problem where we are optimizing it for a particular case. We are not generalizing it over all ranges of epsilon. So, and
Okay.
we are learning tau from epsilon B and H. Did it help, Kamal, or should I?
I'm still like, if it is only one, if it is not parameterizing epsilon, so it's a constant basically.
Yes, it is constant. It is
so
constant.
It's not actually a tau is not actually directly function, it's constant value. So it's not changing the epsilon. So I don't know why required to be an input.
It has to be input because because depending on epsilon, we will obtain the value of tau and then the U.
But
Let's
you're not
say,
changing.
let's say if you're saying that we can directly take it in the loss function,
Yes.
then what will be our input? And then if you think that x comma y can be input, then it cannot be, because tau is not a function of x comma y here.
But tau is,
this is Amya. I think Kamal is asking where is epsilon coming in your tau?
Okay, because if you see the standard formula of tau, even for 1D cases, then it was depending only on the, here is the formula for tau. It depends only on H, B, and epsilon.
Okay, so through Pecklet number it is coming, right?
Yes.
So that's what he was asking.
Oh, thanks a lot, Amir, for helping with that.
Okay.
Thanks.
Okay, thank you.
Okay. Yes, so I was explaining the baseline techniques which we have considered to compare the performance of the proposed technique. We are taking 4 techniques. 2 of them are the conventional SUPG FEM based scheme, wherein in the first we will use the standard formula of tau, which we have already seen for the 1D case, and the second one where we are normalizing the value of tau with the gradient of U, and the other one is the PINS and the variational neural network based schemes for solving PDEs. We are considering 4 types of example with the different complexities based on the presence of the interior layer and the boundary layer. In the first example, we have boundary layer. In second, also we have boundary layer, but we have convection velocities in X and Y both. In the third example, we are having interior and boundary layer both. And in fourth, we have only interior layer. For all these 4 examples, we will show the prediction from the SPD-NET2 and the kind of solutions which we have obtained from them. So for the first example, which is a very basic example, wherein we have a constant source term and the convection velocity is only in the X direction, that is B is equals to 1, 0. For this case, the exact solution for a second order convection diffusion equation looks like this for these coefficients. And this is what we get this is the solution which we obtained from the standard formula of tau, and C is the solution which we have obtained from SPD-NET2. And in the last diagram, we can see the values of stabilization parameter obtained from SPD-NET2. In the second example, this case has source term, variable source term, which depends on the value of U, and F is calculated. So this is basically herein we are obtaining the value of F by substituting this exact solution for U in the equation, and B has convection velocity in both X and Y direction, and the value of U on the boundary is 0. For this is how the exact solution looks like, and this is the tau predicted from the SPD-NET2. And few of you may have a question that why the stabilization parameter is high in the region where there is no boundary. I'll explain this part later on. So here we are comparing the oscillations in the solution obtained from a standard tau and the SPD net 2. In the standard tau solution, we can clearly see the oscillations near the intersection of the boundaries from these two directions. Whereas these oscillations are not available, we could not see these oscillations in the tau in the solution obtained from SPD net 2, which we can see in this zoomed version. In the third case, there is no source term and there is a discontinuity in the boundary value. For this is how the exact solution looks like. And this is the value of tau obtained from SPD net 2. And here we can see the comparison of the oscillations in the numerical solution. Even at this intersection of the boundary, if you compare these two diagrams, then we can clearly see that in the numerical solution obtained from SPD net 2, the oscillations are minimal. In the last example, wherein we have a discontinuous source term, this is how the solution from these two techniques look, and this is the value of the tau predicted from SPD net 2.
Sangeeta, do you also have the plot for tau SUPG?
Tau, I have those values. I can show you the values. Like here in this table, I'm comparing the values. So for all these examples, in this column, we can see the values for tau SUPG, like the standard formulas value. And this is the range of values which we have obtained.
For what?
For different example 1, 2,
No, I just
3,
want to see tau SUPG versus your tau SPD net values comparison for a fixed problem.
Yeah, that's what I'm saying. So let's say, for example, 4, the value of tau SUPG was 4.90 e to the power minus 3. And the range which we have obtained from SPD net 2 is from 0 to 7 e to the power minus 3.
Okay. No, have you plotted these on the computational domain?
No. Actually, yeah, that's a better suggestion. I should have done it on the diagram itself. But since it was a single value, yeah, why I did not do, because this is a single value, and this was a
this will change as per the your Pecklet number, right?
But we have kept the Pecklet number same for doing this comparison for both of them.
Okay.
Yeah. So why am I putting a range here? Because from SPD net 2, we are after doing the prediction, we are doing the gradient normalization to obtain a local value of tau. So we did not have a single value to compare against what we are getting from the standard formula of tau of SUPG.
Thank you.
Yeah, but that's a good suggestion that I should plot it over this diagram itself to see the threshold, at least the difference between the two. Yes, so like initially I mentioned this. So above we can see the value of the residual. By residual, I mean the strong form of the residual for all the 4 examples. And in the below diagrams, we can see the value of tau hat predicted from the SPD net 2. And for this example, which I was discussing earlier, that why it has a higher value of tau in a non-boundary region. It is because in the non-boundary region, the value of the strong residual goes to 0. And the stabilization term in the SUPG is a product of the stabilization parameter and the strong form of the residual. So since the value was 0 here, so it doesn't matter even if we have obtained a higher value of tau here. So it won't affect our solution. For all these aberrations, like here also, we can see a higher value of tau, but because of 0 residual value, it won't affect the solution. Okay, so for us to have a quantitative comparison of the proposed technique with the other techniques, we will be considering 4 kind of error
Sangeeta,
metrics.
can you go back to this?
Yes, I'll go.
Yeah, I mean, in the third example, why your tau is large in the region where your solution is smooth? Yes.
Yeah.
This is away from the boundary layer, right?
Yes.
You don't need a stabilization in that region.
Yes. So that's what I'm saying. Because in the SUPG weak form, since we substitute the predicted value of tau in the SUPG weak form to obtain the final solution. And in the SUPG weak form, in the non-boundary region, the strong form of the residual goes closer to 0. So this whole quantity is what is responsible for stabilization in the scheme. So it won't affect the solution there. Or probably it is coming higher here because in the loss function, we are not getting any input from the non-boundary region, because there won't be any loss as such.
But I think when you minimize it, you should, anyway, your solution is almost smooth, right? In that region.
Yes.
Maybe,
yes.
I don't know, close to 0.
Yeah, I mean, not solution is not close to 0, but the gradient of, the strong form of the residual is close to 0.
Okay.
This is the residual plot. So solution will have some value there. So solution is close to 1 here in this region, for example, 3 in this entire region.
Okay.
But it is because of the residuals value 0 that it doesn't matter.
No, usually we see that you have the stabilization parameter non-zero in the region you have high gradient like boundary layer, and away from it, it almost negligible. You don't need stabilization.
Yes, that's the thing.
So, but that doesn't reflect in your tau.
That's it won't reflect in the loss. But yeah, ideally it should not be there. Ideally, it should be like similar values of, like, it should be 0, almost 0 tau in the at least non-boundary region.
Okay. Thank you.
So these are the evaluation metrics which we'll be using to compare the performance of our proposed techniques with the other baselines. The first one is the L2 error, and the second is relative L2 error. Third is H1 seminorm, and the last one is the L infinity error. So in this table, we can see the relative L2 error values for these 5 techniques. The first one is PIN, and we have also considered Varnet, because Varnet was an extension after the PIN for which uses the weak form of the equation to which minimizes the weak form of the equation. And 2 other techniques. The first one is standard SUPG, and in the second we normalize the value of standard tau with the gradient of u. And for all these 5 techniques, if we compare the performance in terms of relative L2 error, small L2 error, then we see that the performance of SPDNet2 for all the 4 techniques is doing better in terms of relative L2 error. Herein we are comparing the computation time which it takes for the final solution in case of SPDNet2, Varnet and PINs. We have not compared it against SUPG because that's a one epoch scheme, because therein we know the formula of tau and then just solve it. So for these things, if we compare the computation time, then we can see the computation time taken by SPDNet second is the minimum, because here we are getting a faster convergence than Varnet and PIN. In SPDNet2, there are a few limitations. For example, first of all, we are predicting same stabilization value for the entire domain. We localize it like later on after doing the gradient normalization. And secondly, what happens if the gradient of u value goes to 0? In that case, the value of the stabilization parameter will blow up, as we have already seen in some of the examples which I showed in comparison with residual and the stabilization parameter. And thirdly, the SPDNet2 is only applicable to cases where the convective velocity is a constant, because we only consider epsilon, b1, b2, and h. So as to remedy all these limitations, one way is to predict a cell-wise stabilization parameter and to include the gradient of u in the input to the neural network. But if we predict a cell-wise stabilization parameter, then the neural network weights will scale up with the number of cells in the domain. So for that, we should share the neural network weights across all the cells. And the best way of doing it is to use a convolutional neural network to predict a cell-wise stabilization parameter, which is our next technique, SPD-CONNET, which I'll be explaining in the later slides. In SPD-CONNET, we will take the equation coefficient, mesh details, and then we will use Galerkin technique to obtain the instabilities in terms of gradient of u, as we did in SPDNet2. And then all these 3 quantities will be an input to the neural network. And this from this neural network, we will obtain the value of stabilization parameter. And this stabilization parameter will be used to calculate the U, and then we'll calculate the loss. And loss is the same as what we used in SPDNet2. So here in SPDConNet, we can see now tau is a cell-wise tau, and it is a function of epsilon v1, v2, h, and the norm of the gradient of U. In this diagram, we can see, so this is the given domain where we are trying to obtain this solution. And for we are considering a P2 element, and it has, so it is a triangular element. For every element, we have this value, these values. So all of these values you can consider as a channel to the convolutional neural network. And then we use a 1D convolutional layer wherein we share the weights across all the cells. And then we obtain a cell-wise tau. Herein we can see the comparison, qualitative comparison of the results obtained from the standard tau technique, standard SUPG technique, and this SPDConNet. And in this diagram, we have zoomed in so as to see the oscillations. So we can see, for example, there are no oscillations in the case of SPDConNet as compared to the standard tau solution. Herein we have plotted L2 error for two cases. The first one, from this experiment, I'm trying to show the effect of the crosswind derivative term, which we considered in the loss function. So you can see with the standard loss function, the L2 error is always bigger than what we get from the crosswind derivative, inclusion of the crosswind derivative term for all the examples. Is anyone saying anything? I can't. Hello.
You can continue.
Yeah, thanks, Sangeeta. So here in this table, we compare the performance of standard tau, VARNet, and SPDNet2 and SPDConNet in terms of these 4 error matrix. And for all the 4 error matrix, we can clearly see that the performance of SPDConNet is not just better than standard tau and VARNet, but it is also performing better than the SPDNet2 case. Herein I am showing the tau predicted from SPDConNet, and this is what we have obtained from SPDNet2. And this is the comparison of the computation time taken by SPDConNet, SPDNet2, VARNet, and PINS. For all the cases, we can see that the time taken by SPDConNet is the least, and it's a bit closer to SPDNet2's time.
Sangeeta, just one question. Go back to the slide. What's the point here to compare your SPD net computational cost with others? Because as far as I understand, your SPD net consists of 2 things. One is your ANN network, which is trying to find the best tau, and another is FEM, right?
Yes.
So here you have to compare with FEM cost, not with PINS, VARNet, or right?
Yes. Yeah.
So basically, you are improving FEM. I mean, stabilize FEM technique.
No. Yes. Okay.
So what's the point of comparing?
So why have I not compared it against FEM? Because SPDNet2 and ConStepNet already include FEM steps. And if you compare the timing taken by FEM, then it will be nothing against this, because here if it is taking, let's say, 500 seconds, then for FEM it will be like 1 or 2 seconds.
Exactly. So that's the point here. So you are improving FEM. You are not improving PINS here. Right?
Yes, we are improving FEM. So the whole point of doing this plot was to show that either using a purely PD solver for SPD or using FEM, using a hybrid scheme helps us even in time for us. Because by using that loss function, we goes closer to the convergence faster than by what we get by using PINS or VARNet. So for SPD's case, when I use either PIN or VARNet, even for 6,000 epochs and 10,000 epochs, we could not see the convergence in terms of the L2 error. So that's why we have done this plot, that by using this kind of loss function and this kind of hybrid screening, we can quickly go closer to the optimal solution.
Although it's hybrid, basically what you are doing is to improve the FEM, right? So
yes.
Of course, then there are all the issues with the traditional method. I wouldn't say issue, but mesh generation and all, everything will come into picture.
Yes.
And then you cannot compare with pin because it's a mesh free method.
Yeah, it
So
makes sense.
I
Yes,
think
it has its own advantages.
you need to show the advantage of your scheme for compared to FEM, stabilized FEM method, not compared to pins.
So in
right?
terms of time, we can never do better than FEM because
Exactly.
our every epoch,
So the point is you are training your tau for every epsilon, right?
Yes, for every epoch.
Exactly. And in terms of, if I see the advantages in terms of accuracy, they are almost comparable with traditional SUPG.
Yeah, we are doing better than them,
right?
at least one order better.
Yeah, but then you are also paying for that.
Yes, definitely.
Exactly. So here you need to show the advantage of your scheme against the traditional stabilization methods.
Yes, so like in terms of only in terms of the errors we can show the advantage, but for time we don't have any advantage. We are actually paying in terms of time.
Exactly.
Yes.
Yeah, thank you. Go ahead.
So in the last, we have done the mesh refinement analysis for this scheme so as to check if it is numerically consistent, and we have obtained the optimal order of convergence for P2 element. And lastly, I would like to show the solution which because SPD ConNet is capable of cases where the convection velocity is a function of any of the independent variable, either X or Y. So here we have taken P to be minus Y comma X. And because in SPD ConNet, we are taking the input cell wise. And with that, this is the kind of solution which we have obtained for this variable convective velocity case. It is to show that yes, the SPD ConNet can take care of all the complex cases of equations. So as to conclude my presentation, we have proposed ANN edit solvers, which are accurate than both ANN based PD solvers as well as the heuristic based stabilized finite element scheme. And of the three techniques which I showed, SPD ConNet is the most promising one, as it allows the localized tau prediction with minimal parameters because we are using shared weights. And lastly, SPD ConNet can be used for equations with variable coefficients, and all the three techniques achieved optimal order of convergence for L2L. This is all from my side. I'm open to questions if there is any, and these are the future work which can be done done beyond what I have done in my PhD. So if someone wants, they can extend this work for time-dependent convection diffusion equation, and they can derive the stability analysis for the proposed networks. They can also augment SPD ConNet scheme with the adaptive mesh refinement, and these proposed schemes can be deployed for different problem cases like two fluids for viscoelastic fluids or a multiple stabilization parameter case. Yeah, thanks. This is all from my side. I'm open to questions if there are any.
Thank you, Sangeeta. Do we have more questions for Sangeeta? I think we already had a good discussion during your presentation.
Yeah, thanks a lot. I got a lot of suggestions from the audiences. Thanks.
Okay. So if not, yeah, we'll move into our second speaker. Thank you, Sangeeta, for tuning in and for giving us this presentation.
Thanks a lot, Somnata, for this opportunity.
So we'll move into our second speaker. Our second speaker is Gianluca, and he would be talking to us about parsimonious physics-informed random projections neural networks for solving forward and inverse problem. He has a bachelor's degree in maths and master's in applied mathematics, and he's currently a third-year PhD student at Scuola Superiore Meridionale, Italy, University in Italy, where he's working on modeling and engineering risk and complexity problems. Currently, he's a visiting student at Johns Hopkins University, where he is working with Professor Yanis Kevrakidis. With that, please join me in welcoming him for the presentation.
Hello, everyone. Thank you for the kind invitation. It's a great pleasure to be part of this series of seminars. So, as you said, I will talk you about a topic that is at the intersection of numerical analysis and machine learning. In particular, I will present you physics-informed random projection neural network. So the outline of presentation is the following. I will first start with motivation. What are the main challenges in solving forward and inverse problems for complex systems? Then I will introduce our scheme, the random projection neural network, and I will explain why we call it parsimonious. So we will see how to solve the forward problem, including steady-state problem for PDEs, and also time-dependent problems, T for Ds, DAs, and PDEs. Then we will see also two examples of solving inverse problem. For example, reconstructing PDEs, Fitzhugh-Nagumo PDEs from lattice-Boltzmann simulation, and we will see also an agent-based model and finance. And we'll draw some conclusion. So let's start with motivation. As scientists, we are fascinated about the complexity of the world around us, and actually complex systems are quite everywhere. We can find them in biology, we can find them in mobility, neuroscience, climate, just to name few. But the problem is that to describe the emergent behavior of this system, usually we don't have explicit available closed form equation to describe them. So usually what we have to do is to solve an inverse problem that is the opposite of a forward problem, and we are interested in both. This is two sides of. So the forward problem is when we know the model and we want to find a solution. Look, the unknowns are in red here. So we may have ODEs, PDEs, or DAs. While for the inverse problem, we just have data, just have trajectory in space and time, and we want to reconstruct, let's say, PDE, and this can be either black, gray, or white box PDE. So we want to find the relationship and maybe also some parameter to close the problem. But we have open challenges in both the two directions of this, because, for example, for forward problem, if we have to solve a 9-dimensional system of PDEs, to get a fast and accurate solution is not trivial. And again, for the inverse problem, we may have some technique to use pen and paper to find mean field approximation, but yeah, we won't find with machine learning better closure. But in particular, the main question that we want to address here is if machine learning can actually beat traditional numerical analysis methods for the solution of stiff ODEs and PDEs. There are actually several techniques that arisen in the last few years for solving ODEs and PDEs, like deep learning, Gaussian processes, physics-informed neural network. But there are many issues. For example, they lack in numerical accuracy. They may require a high computational cost, and usually they also require extensive computational resource, including large-scale GPU system. Also, another problem with this technique is that we usually compare them among themselves, but what we have to compare them with is well-established numerical solver. And it is what I want to show here today, that for the first time, actually, machine learning can be comparable, and several cases can be also better with respect to well-established traditional stiff solvers. Most importantly, also in terms of computational time. So what is a random projection neural network? It's a very simple idea. As you can see, this is just the ways that connect the input and the hidden layer are randomly initialized, they are fixed, and they cannot be trained. And the only ways that can be trained are the ways that connect the last hidden layer with the output. This seems a very simple idea, and so the first impression that we can have is actually that this is just a stupid idea. And this was also what Gianluca, that is one of the godfathers of artificial intelligence, wrote on Facebook in 2015. So actually he wrote, connecting the first layer randomly is just about the stupidest things you could do. I think this is a good starting point to start this tool. So let's see random projection neural network. We will consider a very simple structure, just a single hidden layer neural network. We have weights alpha that connect input and hidden layer and biases and weights. For this single layer neural network, the classical one, we have universal approximation. As also was proven by Lesno, this holds if and only if the activation function is not a polynomial. So we have a broad possibility to show the activation function. The problem of all this theorem of universal approximation is that even if they say there exist some optimal ways, internal ways, external ways, and biases, they exist, but there is not a clear way to how to find them. So we have to proceed in a iterative process, a training process, usually gradient descent algorithm that may include backpropagation, Adam, BFGS, Leverman-Marquardt. But we have a non-convex optimization problem. So what we can find are only suboptimal solution because we are usually trapped by local minimum. And also, if we want to solve large-scale neural networks, then we have a cost of dimensionality in the weight space, and this may require hours or even days to train a large-scale neural network. So we can explain this by thinking to life. This is a cartoon from Steinberg called Course of Dimensionality in Life. In life, we cannot take optimal decision because we have to be in the right position in space, in the right moment in time. We have our duty, we have our doubt, and we cannot collide everything and take an optimal decision. There are too many variables and too many constraints to decision in life. And this is actually what happened also in the course of dimensionality neural network, because we have this to decide the number of neurons, we have to decide the number with the layer. These are integers, so we cannot optimize easily with respect to integer. We have a lot of hyperparameters like learning rate, patch size. We may have other hyperparameters in the activation function. And also we have to deal usually with high-dimensional problems, also a course of dimensionality in weight space. And as I said, this is usually a non-convex optimization problem. So optimal solution of neural network usually do not exist. We can get just suboptimal solution. Given this, let's try to find good suboptimal solution with random projection neural network. So we fix internal weights alpha and biases beta, and the only degree of freedom, so the only unknown, the only parameter that we can train are the weights that connect the detail layer and the output. This is a simple idea, and this was already proposed in the prehistory of neural network. This was called Gamba perceptron and was proposed by Rosenblatt and was also studied by Miske and Pepper. This was also proposed as an algorithm to just adapt the weights here, and this was called pocket algorithm or distributed method proposed by Galland. Let's say that now the real network that we want to address are this one. The first to propose here, this was Smith with random weights neural network in 1992. Then also random vector functional link network proposed by Pau in 1994. But this was kind of forgotten of this thing and was rediscovered by Jaeger in 2002 with a similar idea. This is a recurrent network with the name EcoState neural network, and now they go all under the name of reservoir computing. And then after some years, arise this fancy name, stream learning machine, proposed by Wang in 2006. And actually, his paper got a huge amount of citation, but also this is a little bit controversial because he got a lot of plagiarism allegation. So we don't like all this name. We think that everything can be actually traced back by Johnson-Lindenstrauss theorem that actually says if we have a set of endpoints in RD and we have a given threshold, always exists a map, and this is a generic map from RD to RK, such that we can preserve the distance in the embedded space with this accuracy epsilon. There are many of such embeddings, but one of these embeddings can be simply a linear projector where we have a random matrix with random variables, and these random variables are normal random variables. With this approach, actually, we can prove with high probability that we can preserve the norm of the vector. So look, the theorem was deterministic, but the proof relies on probabilistic techniques. So I will try to explain just a sketch of the proof. We can consider the matrix where R, R2, Rk are the rows of this matrix. So the small Rij are the elements of the matrix that are normal random variable. And let's take a vector in Rd. Let's consider the map and take the L2 node. This will be written in this way. So if we take the mean of the map, then we can put the mean inside the sum, and then this will be just the mean because they are identically distributed. So then, since we know that if we sum to a normal distribution, we get again another normal distribution. If we consider the scalar product here, this has each element the sum of these elements that are each one normal distribution. And so at the end, this is distributed as a Gaussian with variance the norm of the vector. So this means if you take the mean of the square of this will be just the norm of the vector. So the mean of the map will be the norm of the vector. And in particular, since these are all identically distributed Gaussian variable, this happens to be a chi-squared random variable. And for this, we have this lemma. So that says that chi-squared random variable actually are concentrated around the mean. As I proved, it's just the norm of U. But up to now, we are working only with, let's say, Euclidean distance and with linear projection. But in general, when we work with data, we know that we may need other kind of distance, other definition that may involve some kernel. And this is usually called kernel trick, where this kernel actually define implicitly a lifting operator phi and also an inner product. And this kernel approximates this inner product. This is the trick of using kernel. The problem of using kernel is that if we have large training set, this usually incur in large computational time and storage costs. So the idea here is to use random feature to show that we can actually approximate this inner product by just random feature maps. This indeed was proven again by Raimi and Recht in 2007. So if we consider a kernel that is positive definitive shift invariant kernel, we can take just the Fourier transform of this kernel, and this will be a probability distribution function. So we can draw sample from this probability. This will be the weights. If you see, this is a sort of hidden layer of a neural network because we have just cosinus and sinus activation function. So this is called random Fourier feature also. And with this vector, we can actually, with high probability, approximate and be, no, actually approximate to preserve the kernel distance. Okay, so now with this approach, everything became more simple. We'll have a very simple algorithm, for example, for regression problem. We can just compute the random matrix, given the activation function and the random weights. We will compute this matrix, and the regression problem will be just a linearly squared problem in the external weights. So actually, we can solve this with, for example, Moore-Perouse pseudo-inverse, getting also a regular solution. And this, as you can see, this will be faster, this will be simpler, optimal. And also, if we have more neurons that sample points, we can also look for minimum non-solution. So we will have also regular solution. There are still some drawbacks in this matrix because this will be usually full matrix. It's not a sparse matrix. And also, generally, this is a ill-conditioned matrix because we are just randomly producing functions, and this can be also similar between them, or can be very far from what we want to solve. Actually, we have also universal approximation for random projection neural network, and these are sort of forgotten theorems again. This was first proven by Baron in 1993, and then again proved, but in mean with a better convergence by Igelnik and Pau. And then also again, Raimi and Recht proved that we have universal approximation in probability with high probability and with a convergence of 1 over square root of n. So now I have to explain why we need parsimonious random projection. As I said, the matrix is usually ill-conditioned, and if we use two, actually we have this random variable to sample. Usually we sample them from uniform distribution, and we have to set the bounds of this distribution. If we set this bound too low or too big, then the performance of random projection are not good. So what we have to do is to experimentally tune this parameter. So for example, if you consider sigmoid activation function, you can see that changing beta, we are actually changing the position in space of the function. And changing alpha, we are actually changing the steepness of the function. So we don't want functions that are too much steep. We don't want functions that are too much linear. And we want to set the center, that is the inflection point, that can be defined as minus beta I over alpha I that are internal on the domain where we are working. We don't want functions that just vary outside of the domain, but they should vary inside the domain. So experimentally, we tuned this parameter that looks proportional to the number of neurons n, but also scale with the dimensionality of the input. So it goes 1 over d. This is a sort of course of dimensionality. Then found alpha and selected the center that we want to give to our function, we can just find beta with this expression. But as I said, there is a course of dimensionality in doing this. We cannot really explore if we have a d-dimensional input, a d hypercube with all the centers, because this would require a number of neurons that is proportional to 10 to the power d. So in the case of high-dimensional data, if we do this assumption, so that the data are actually intrinsically embedded in a lower dimensional manifold, and this is a reasonable assumption for many regression problems, we can describe again the inflection points that for a negative dimensional input will define an hyperplane. So for example, here we have a three-dimensional input, and we can see the level set of a sigmoid. So this is a rich activation function. You can see that along this direction, the function is just constant, and the variation is only along the direction alpha I that define the direction of the hyperplane. So the goal that we have in mind is to find the center, so the points of that are in the hyperplane that also has to lie on the manifold that we are considering. So to do this, actually, if we have data, we can just subsample the centers to be subsample data so that they will be the centers. But then also we have a problem with the direction. We need that also the direction is pointing inside the manifold and not outside the manifold. So we propose to independently randomly other sample points Ci, and with just computing the differences, we can compute an hyperplane that is a direction parallel to the connection of these points. This will ensure that direction is inside of the manifold. And we then can just get the basis beta as before, just minus alpha I times Ci. So what I'm showing is that in principle, we need an intelligent choice of these parameters so that we can construct smaller network, and also we can get well-conditioned nonlinear random projection. And in this way, the goal is to avoid inefficient training processes. So let's see how we can solve for what problem. The classical numerical analysis, for example, for system of ordinary differential equations says that we can approximate a differential equation with this integral form. And we want to approximate this integral by first approximating the function f using some polynomial interpolation and finding the integral of the polynomial. So as you know, there are a lot of methods, explicit Euler, Runge-Kutta methods, but we can have also multi-step methods like Adam-Bashford, Adams-Moulton, explicit and implicit. And we may have also backward differentiation formula that actually is the formula used in OD15S for stiff problem in MATLAB. So our goal is to solve stiff problem. Stiff problem, there is not a general, let's say, definition, but as was said by Champine and Gear, if we use a code that aims to non-stiff problem, then this is inefficient for no obvious reason. There are actually some reasons. For example, we may have some stability requirement that constrain to mask the step length. If we are dealing with components that decay much more rapidly than others, for example, as happened in chemical reaction, stiff ODEs, this can rise stiffness. And also, if we are solving PDEs and we are using the ODE, a finite difference discretization or any discretization, this will lead to a system of ODEs, but that is stiff. We are also considering steady state problem for PDE, so boundary value problem, in which the boundary is defined here, and this is the operator. And we have several techniques also to solve this. We may use finite differences, we may use Galerkin finite elements, where the solution is actually found in these ways that looks similar to what we are looking for in a neural network basis function, let's say. And there are also other methods more advanced, like spectral methods using Chebyshev expansion. But this can be also solved with machine learning, both the forward and reverse problem. Indeed, as was proposed by Rigo Martinez in group of KDD, this was the first example of recurrent network. in which they was using approximating a Runge-Kutta integrator. Also in Gonzalez and Garcia in the group of Kikidis, they proposed again the first example of convolutional neural network in which they was using finite differences as let's say to learn PDEs. And then the main reference for solving for the forward problem is Lagari's sample studies in 1998. And nowadays, with new algorithms and new computational power, there is a new rediscovery and also modern advances. Indeed, we have a lot of methods now to solve PDEs, like deep learning, Gaussian processes, physics-informed neural networks that take advantage of automatic differentiation. And we are also working on a random projectional network for this kind of problem, as we did in Journal of Scientific Computing in 2021. So how a solution works, as also was explained in the previous talk, we have to solve this big minimization problem with respect to some parameters that are parameters, for example, of a network, the weights, and also we may want to optimize with respect to some hyperparameter. In general, the solution can be also a transformation of a machine learning algorithms. So let's see some solution of PDEs, the steady-state problems. In this case, we are considering steady-state problems that also depend on some parameter, so that we can see different solutions, different steady-state solution. In this case, we are using a neural network, a random projection neural network, as trial function of the problem. So we can locate in space, so the points in the domain, but also on the boundary, and we get a set of algebraic equation in terms of the weights of the neural network. These are a system of nonlinear algebraic equation, but we can actually solve just using, for example, a Newton method. So this means we need update of the weights. So this is iterative, it's not a single shot solution, but actually we know that Newton, we can expect that we have a quadratic convergence, so this may require only 3-4 iterations to converge to a desired tolerance. We can also find solution for different value of the parameter, but if we have a bifurcation, then we know that the Jacobian will become singular, so we cannot solve the problem there. And we have used a simple pseudo arc length continuation, which we define an arc length condition. And yeah, we augment the system, and now we can solve also with respect to this. Notice that this is done again with respect to the weights of the random projection neural network. So as example, I consider a nonlinear viscous burger in one dimensional with two kind of boundary conditions, Dirichlet and mixed. And we also consider Liouville, Bratu, Gelfand PDE, both in one dimensional and two dimensional, both in a square domain and a circular domain, as was proposed in this paper by us. So let's look to burgers. This is a simple nonlinear equation. We consider a Dirichlet boundary condition. We have gamma on the left and 0 on the right. And we also Neumann on the left with minus theta and Dirichlet on the right, 0. Let's look to the Dirichlet case. In this case, we can prove that there is a unique solution. So we have a reference to which we can compare. Changing the parameter nu, the viscosity, we can get, if you go to a smaller viscosity, we can get actually a boundary layer, as was also said in the previous seminar. So this became more stiff, and actually finite difference and finite elements can generate spurious oscillation. So we can solve this problem. We have in yellow the convergence of finite differences with respect to the collocation points. We are the L2 error. You can see that also the convergence in purple of finite elements, while you can see that with using sigmoid activation function and radial basis function, we have a very good convergence. We can get actually to a very low accuracy that is of the order 10 to the minus 15 in the L2 error. So this is very close to epsilon machina, and this was also able to do when we have a boundary layer. And so as you can see, this was the first time actually that a machine learning approach can outperform finite elements. But why I can say outperform? Because if we look to the computational time of this approach, actually we can see that we need less than 1 second, an order of time of order 10 to the minus 3, 10 to the minus 1 for bigger grid. And this is comparable with finite differences, but sometimes it's even better of finite elements. So we can get in a less computational time, much better solution. Let's look also to the mixed case where we have two solutions, two analytical solutions. One is stable, that goes to 0 actually, here, and one unstable that goes to plus infinity with a very steep boundary layer. So for this, we have reconstructed the whole bifurcation diagram, where we have a saddle node bifurcation here, with all the methods, finite difference, finite elements, using sigmoidal activation function and random function in random projection and random network. Also going where the solution became very stiff and with a very high boundary layer. This is the unstable solution. And we got a better approximation of the turning point using our proposed approach. And indeed, we have an analytical solution also for the turning point, and we can get a convergence in that goes as 10 to the power minus 10, outperforming both finite elements and finite difference. Let me skip this one. Let's go to other problem. This is BRA2 problem. We also get a good result. Let's go to the time-dependent problem. So in this case, we have this paper that is recently published, and we are particularly proud because this was selected as an editor pick in chaos. So we consider not only ODE, but we consider initial value problem in a linear implicit form, where we have a mass matrix that multiplies the left-hand side. This can be also singular, so this includes also DAEs, differential algebraic equation. And the solution that we look for this problem is not only a neural network, that is this n, but this is multiplied by t minus t0, such that for t equal to 0, this is Zi, and Zi is the initial condition. So this explicitly satisfies the initial condition. So we also use a Gaussian radial basis function for this network, and where in principle we have a random projection on the input, and then we have also center and shape parameter of the Gaussian. We put to 1 this weight and to 0 this bias, so that only random parameters are the center of the Gaussian and the shape parameter. And we have appropriately chosen the uniform distribution for this shape parameter. Particular for this problem, we can prove a theorem for this framework using Gaussian basis function. We can have a uniform convergence with high probability to the solution profile in this in the closed interval. And the order of convergence is 1 over square root of n. And the proof is simple because if you think to the integral form of the solution and to the trial function that we are looking for, you can see that both S and I, so the difference will cancel this. And actually the neural network is not approximating the solution in this case, but is approximating the Lie-Carping of integral. So this is actually turned out to be a Monte Carlo quadrature method. So this is why we get this convergence. Also, to deal with stiffness and sharp gradient that arise in the solution of ODEs, we also propose an adaptive scheme. So we divide the interval in many subintervals. Let's assume that we have solved it in this interval tk minus 1 to tk, and we are looking for a solution in tk to tk plus 1, where we have an adaptive step. So tk plus 1 is changing based on a simple control problem that takes the previous error made by the last Gauss-Newton iteration, and in this way we can adapt the time step. Then we, for the first time, also propose a way to give an initial guess for the weights that is based on numerical analysis continuation. Indeed, if we, for example, set the weights to 0, this is correspond to a 0 continuation. So we start with a flat solution. While with the continuation that we propose, this is like a first order approximation. And this gives a better computational time and a faster convergence to the method. Then we used the van der Pol problem that is here with these two equations, where mu is the stiffness parameter, to parsimoniously shows the bounds of the uniform distribution of the shape parameter. So in particular, we have that the shape parameter is usually drawn by a uniform distribution where we have 0 and alpha max, and we want to optimize alpha max. We found analytically that this alpha max should be proportional to the number of neurons squared divided by the length of the interval squared, and we put this 1/c squared as proportional proportionality constant. And actually we use it as loss function, not only the error, but we use it a bias variance trade-off loss. We solve it for different number of neurons and for different values C with an extreme search. And we found that the optimal values are around these bounds here. You can see that we can only do an extensive search. We cannot do optimization, but because there are too many local, so we will be trapped everywhere. But if we want to find this, we have to do an extensive search. So we not only found the best, we have also given the time here. So you can see that the best time is on the bottom left corner. So this means that the best solution is on this line, and the fastest one is here. So we actually selected once and for all the number of neurons. So we also optimized the number of neurons, and we also get the best, let's say, optimal value C that is taken to be 12. So we have solved several benchmark stiff problems for ODs and DAEs, including steep gradients, van der Pol, Robertson, index 1 DAEs. We also compare with the Lotka-Volterra ODs that was proposed in the DIM of deep CDE, and also 2 PDs, Allen Kahn and Kuramov-Zivazilski. What is important is that we compare in terms of approximation accuracy, but also in terms of computational times. And we compare it with well-established solver, OD23T, OD15S of MATLAB, and also with deep learning of deep CDE. So for the van der Pol that I introduced before, we get a very good solution. In green, we have the random projection that outperform in convergence OD15S and OD23T. Then we have this Robertson index value problem that is a chemical reaction problem. We consider the DA version, so when we have also an algebraic equation is a conservation law. For this, the random projection neural network got the similar result to in terms of time execution and L to error, and outperformed OD23T. Then the problem where we compared with deep CDE is this Lotka-Volterra problem. It's 2 ODEs. It's a stiff problem. We use a different tolerance to find different solution. You can see that we can get L to error that goes to 10 to the minus 2 easily to 10 to the minus 5. And the computational time is always less than 1 second, 10 to the power 2 to 10 to the power 1. While when you use deep CDE, you have to set the number of hidden layers. Okay, we selected 3, 4, 5, 6, and respectively 8, 16, 32, 64 neurons to get a sort of convergence. An acceptable result was gotten for the last structure with an L to error of 10 to the power minus 3. But to take this result, this takes 30 minutes. So actually, our result is 20,000 times faster than deep CDE. So let's look also how we can solve PDs. This is an Allen Kahn PD, famous for phase field models. We have a Dirichlet boundary condition. This is the initial condition. We solve for a long time. Ni is 0.01, and this is a final difference discretization that leads to a system of 100 stiff ODEs. So in this case, as you can see, we have a metastable solution because it looks stable up to a long time, but there is a sudden change, and from a 2-yield solution, we go through to a 1-yield solution. This is the error of random projection for a tolerant 10 to the minus 6. And we can see that we have random projection OD15S that is better than random projection in terms of computational time, but still we can get a solution in very few time for this difficult problem, just 1 second, while still outperforming OD 23T. So to give another comparison, we can also comparison using the same tolerance, all the methods. So this is the solution of random projection for 10 to minus 6, and this is the solution of 10 to the power minus 6 for OD 15S and OD 23T, and we can see that in terms of factor error, infinite error, and mean absolute error, we are outperforming the other scheme. So we are just a little bit slower because the system is high dimensional, but the solution is better in accuracy. We did the same comparison also for Kuramoto PD's problem, where we have a chaotic regime. These are again the solution for 10 to the power minus 6, and this is the random projection solution. Is we can get a low error, and indeed also in the table you can see that we are outperforming the other two schemes. So this is just a QR code to show you the code is a GitHub repository, randifnet. This is me, and you can find random projection for Steve4D. So if you want, use this code and cite us. So let's go to the inverse problem now. In the case of the inverse problem, we have to make some assumption. We have, in principle, we know that some equation exists, but we don't know how this equation are. So the most general assumption that we can make is that the system depends on an integral PD, not just a PD. So if these are the fields that we are considering, let's say that we have m different fields, then we will need to find m different nonlinear operator. Epsilon will denote a parameter. I are some integral on some patches on some subdomain of the domain. So we may have many feature computer like this, and we may have also many, these are let's say global feature, and the derivative gives us local feature. So we may have pure or mixed derivative up to any order need. So if we collect all these possible features, space, field, possible integral, and all possible derivatives, we have a very high dimensional feature space in which we have to find which are the dominant feature. And also we have from data solution in space and time. So each point in space and time correspond to one point in this high dimensional space. So starting from this full input data, so this high dimensional space can be prohibitive, and we have to extract only the relevant spatial derivative and the dominant features. This can be done in several approaches. We used an automatic relevance determination with Gaussian processes, and also we used the parsimonious diffusion maps approach. So in this way, we can minimally parameterize the dominant feature and finding the intrinsic embedding where this feature lives. For solving an inverse problem, we can use neural network, as you can know, it was also proposed by the group of editing chaos in 2020. So this can be both a classical neural network, but can be also a random projection neural network. So you can think that these weights are fixed and we just optimize with respect to this one. This network was actually a convolutional neural network. Indeed, we can estimate with the finite difference density other derivative of the solution. We can also use many patches to give some integral features, and then from all these features, try to solve this problem, the finding f. So the desired output will be the time derivative of the problem. As example, we'll consider two problems. One is a phase field model in neuroscience, a Field-Nagumo model describing an action potential propagation in neurons. And also we will see an HMS model on financial market with mimesis. So the Field-Nagumo is this one. We have these two PDs, a reaction, diffusion reaction problem, epsilon is a parameter. We know that the PD is intrinsically lives at the macroscopic level, but if we go inside, we can think that in each patches there is a distribution of many particles moving, so a sort of Boltzmann distribution. So we can use lattice Boltzmann to describe here. If we go even more at a fine level, we may have particles that moves inside. So we stick with the mesoscopic level, we do simulation at the mesoscopic level, and then we try to reconstruct the macroscopic Field-Nagumo model. So this is the Field-Nagumo. From this, we can derive the lattice Boltzmann simulation for that is a mesoscopic level. So we can think that we have dummy particles that move inside our domain. So we take many different initial conditions. Each of these dots here correspond to a different initial condition in terms of a different mean of this sigmoid and a different value of the parameter. So we sample all this space in terms of initial condition and parameter, and we do a regression. We're using both feed-forward neural network, so deep learning, and random projection neural network, getting similar results in terms of regression coefficient. The main difference is that the training time for deep learning needed 4 hours, random projection neural network needed 8 minutes. So you can see that this is 50 times faster than classical neural network. We also selected, as I said, with Parsimonious diffusion map, what are the main features. We can see that the features actually are can be described with just 3 components. These are not linear, so we may need still 3. For the UT, for the first equation, we can see that UV and UXX are the main feature. And for VT, the second equation, you can see that UV and VXX are the main feature. So actually, this is in agreement with the Fitsugunagumo model. So we define this feature selected PDE model. And we reconstructed from these models, finding the steady state of the PDE as I explained before, so bifurcation diagram, using both feed-forward neural network and random projection neural network, and both using feature selection and without feature selection. And they all get good result in terms of turning point, and also of a off point was that was here. So let's look to the second example. We have an agent-based model in finance. Each agent is described by a state variable that is a preference state, a real value between -1 and 1. And this is the equation that describes the agent. And there are news from the market that came. If the agent is isolated, we have an individual behavior that just drift the agent to the center, so to a neutral position. But there are also news from the market that can be both good and bad news. And there are Poisson distributed arrivals of this news with frequency in E plus and E minus, and this generated discrete jump in the agent. So if a bad news arrives, the agents jump on the left, and if a good news arrives, the agent jump on the right. But there is also a reset condition. So if the agent crossed the boundary 1, then we say that the agent buy, and then we reset the agent to the neutral position. As well, if the agent crossed the left boundary, it sells and is resetted to 0. If we consider a large ensemble of agents, we also consider the influence of the other investors. So we have this perception of the frequency of Poisson arrivals is influenced by how many agents are buying and how many agents are selling. So R plus and R minus are the rates of buying and selling agents. And this one actually influences the agent to be more bullish, and while the agents that are selling influence the agent to be more bearish. So actually for this system, we can derive a concise description, but just considering probability density function over the agent. So for this, this probability distribution function, actually, Omurtag and Siforovich in 2016 found an integral Fokker-Planck PDE that is an approximation at a macroscopic level of the problem. But this is an integral PDE because there are these two terms, plus and minus, that are estimated. So the equation is closed with this integral. As you can see, for the solution of this system, we have for different value of G that will be our bifurcation parameter, we have stable solution up to G45 in purple, while if we change, there is a sudden change parameter a little bit more, there is a sudden change, there is a tipping point. So the solution explode, blow up, both for G46 and G47. This is explained by the fact that there is a saddle node bifurcation in the bifurcation diagram. For example, Fokker-Planck is this one in red, but this was also computed in 2012 by the group of delegates with equation free, and actually the two do not coincide. And as you can see also from simulation, the correct one is the equation free. So the Fokker-Planck is just an approximation, qualitatively okay, but not perfect, and we want to find with machine learning a better closure. So again, we used many different initial conditions. Each point is a different initial condition. we run in time for a long time. This is just the preference state, but you can think that this is evolution of the PDF in time. So we got features, for example, first partial derivative, second and third. We can get some integrals, like the one that was used by the Fokker-Planck, and we can do sensitivity analysis using automatic relevance determination, finding that actually the integrals are important. So this is truly an integral PD, that the space is important. So this is an inhomogeneous PD. And the only feature that we was able to disregard was the third order derivative. And this actually is again in line with the Fokker-Planck derived by Omurtak and Siforovic. So these are the features that we selected. And so we want to find a black box model in this nonlinear form with all the features, and we also use the parameter G as bifurcation parameter. We use it for regression to approach one feed-forward neural network with 2 hidden layers and 16 neurons using hyperbolic tangent activation function, and compare it with random Fourier feature network, so a random projectional network. When we use cosinus activation function, we use 350 neurons. We performed regression. We got similar result for both. The small error that you can see is that because we still have some noise in the evolution of the PDE. And the only difference actually is that in terms of training time, we can get a solution with random projectional network in just 26 seconds, while feed-forward neural network required 1,400 seconds. So again, this resulted to be 50 times faster than feed-forward neural network. We can also, once we found the model simulated, and we can see that our model in blue and in black are in agreement with the ground truth of the agent base in green, while the Fokker-Planck is slightly different, as you can see also by the error in space and time. So we was able to reconstruct the right bifurcation diagram, finding a good stable state branch, a good approximation of the turning point. The only difference is that the random projection neural network was also able to find a good unstable branch, while the feed-forward neural network has some struggle of finding for low values of the parameter the right unstable branch. This is because the PD actually kind of explode after a few times. So this was not a simple problem, but random projection seems to be more regular in finding solutions. So to conclude, I showed you that we can use machine learning also in a random projection form to bridge detailed physical modeling and finding macroscopic PDEs. Also for forward problem, we can bridge the gap that there is between machine learning and numerical analysis, especially in terms of computational time, using, for example, random projection neural network. And we can couple our machine learning algorithms with well-established numerical bifurcation tools to study bifurcation diagram and tipping points of the system. So to conclude again, the scheme that we proposed take advantage of random projection network as the Johnson-Lindenstrauss theorem says, and also the Riemann-Recht says, we can bypass this expensive training phase of these classical machine learning schemes. The implementation, if you think, is very simple. It's just a least square problem. So we don't need large scale GPUs. We may do all in a single core processing. The efficiency was compared with well-established solver like OD15S in MATLAB, where finite differences and Galerkin in finite elements, and also with deep learnings. But in all the cases that I showed, we can outperform the traditional numerical analysis and deep learning scheme, and both for the forward problem and the inverse problem, again, especially for computational cost. So let me thank my collaborator, my supervisor Konstantinos Sietos from Scuola Superiore Meridionale, my co-advisor Yannis Krivigis from Johns Hopkins, Dr. Lucia Russo, Professor Yiannakopoulos, Dr. Galaris, and PhD also at Johns Hopkins, Nicolas Evangeliou. So thank you for your attention.
Thank you, Gianluca. Do we have questions for him?
I have a question.
Yes,
Mhm.
Mario, go ahead.
This is Mario from Brown. Nice presentation. I really enjoyed it. I just have a question about the nonlinear, when you solve forward nonlinear problems, that you have for the least square that you have to solve, you're computing the Jacobian first, right? And what solver do you use to actually compute the least square?
Let me go. Yeah. So thank you for your question. Actually, it's interesting. Yeah. So this is not a simple Newton method. This is more a Gauss-Newton method because we use a Moore-Perot pseudo-inverse also for inverting the Jacobian. This is needed because since we have all random function, this is usually, even if we sample well, we still have some ill conditioning in the way we have our function approximation. So we still need some regularization. And this is done by selecting some tolerance in Moore pseudo-inverse. We actually did also with other techniques. You can use QR decomposition with code that makes regularization also. There are codes that are very efficient for that if you have sparse matrix. For example, when we have solved the PDEs, we are using finite differences because finite difference give you a block matrix that is only the block diagonal is not zero. All the other block matrix are zero. So we can use sparse in that case, sparse square decomposition.
Okay, thank you very much, Gianluca.
Thank you for your question.
For your talk.
Okay, sure.
I think we don't have any more questions. So thank you for this wonderful presentation, Gianluca. It was a lot of information. So thank you.
My pleasure.
I would be uploading the recordings of our Crunch seminar today over our YouTube channel. And thank you everyone for tuning in today. And thank you both the speakers. With that, we come to an end of our Crunch seminar today, and we'll see all of you next week. Thank you.
Thank you.